Alright, hi YouTube, this is Mr. Lim here, and this is our video on indicators, so let's get started. Alright, this is what we're going to learn about. Okay, so an indicator, and we actually dealt with a couple of indicators last year as well, but this is a more technical definition. It's a chemical that changes color under different pH conditions. Okay, it works via an equilibrium system where a conjugate acid-base pair exists as different colors. Right? So what does that mean? So you might have a substance which is HX, okay, where X is some sort of like another part of the molecule. Generally, they are organic molecules with water. And because this is a conjugate acid-base pair, the hydrogen will come off the acid and it will form hydronium ions. All right. The idea is that this HX and this X are different colors, okay? And so that when we change the concentration of the H3O plus, if we make it higher or lower, the equilibrium system will shift and the concentration of the HX or the X minus and their colored forms will change, and therefore the color of the system will change, right? So that's the idea behind it. Right, the concentration of the indicator conjugate pair is generally quite low, so it's not a very high concentration of the HX and X minus, otherwise it would be a buffer, and we'll learn about buffers in the next video. Right, so let's move on. Okay, so if the concentration of the hydronium ions change, then the concentrations of the two components of the conjugate pair will change. Okay, so let's go rewrite that out. But we'll write HX plus H2O goes to X minus plus H3O plus. Okay, so if I add hydroxide ions, so the concentration of the hydroxide ions increase, which means that the concentration of H3O plus will decrease. Okay, they'll be consumed by those. All right, if they are consumed, then what's happening? That decreases, so therefore the forward rate of reaction is unchanged. The reverse rate of reaction goes down. Okay, so the reverse rate of reaction goes down because there's less H3O pluses causing less collisions. Therefore, there's a net net forward rate of reaction. Okay, so if there's a net forward rate of reaction, then the concentration of your products is going to increase and the concentration of your reactants is going to decrease. Okay, so therefore, remember that the products is the X minus. It's going to get more of those and it's going to have less of the HXs, which means that it's going to go more blue. Okay, less red, more blue. Maybe it was purple, I don't know. But the idea is that it bears more blue form of it. All right, if you add hydronium ions, effectively the opposite thing happens. Okay, so you would have an increase in H3O plus ions. That means that the forward rate of reaction is unchanged. The reverse rate of reaction would increase. That would make it a net reverse rate of reaction. If there's a net reverse rate of reaction, the concentration of products goes down and the concentration of reactants go up. Okay, and if this if the reactants is HX and the products is X minus, become less blue, more red. Okay, and you can also say the same thing, it'd be less red here. All right, so changes in the concentration will change the equilibrium system and cause change in the concentration of the colored species. Okay, so also another idea is that whenever you're asked to explain this, you should be referring to the colored species by its name if it's given it, or its formula if it's been given. All right, just make sure that when you're talking about a change in color, you refer to the change in the concentration of the species that is colored. Okay. Then the last one, you can work out the indicator's predominant form, or which of the two conjugate pairs is more prevalent, the HX or the X minus, from the pH. Okay, so like often we'll say, okay, well, here's the two forms, which form is more present, or which one is there a greater concentration on in high pH or low pH? Let's go work those out. So at high pH, which means that's effectively basic, which means that you've added lots of OH minus, okay? And if you've added lots of OH minus, the concentration of H3O plus will go down, and then you can go through the entire system again, and then you work out which is the more predominant form, okay? The idea is that from this question, you have to work out from the beginning, okay, at a high pH, right, I've added a lot of OH minus. I'm going to decrease the amount of H3O plus, right? If I was to go through that thing again, therefore the forward rate of reaction is unchanged. The reverse rate of reaction goes down, right? And then there's a net forward rate of reaction. Therefore, the concentration of products goes up, which means that, and the concentration of reactants goes down. Therefore, this being the X minus, this being the HX, the predominant form would be the X minus, would be the predominant form. Okay, which happens to be the conjugate base. Okay. Then at low pHs, which would be acidic, it would be effectively the opposite thing, or the same things that we were looking at before. It would be the opposite form. It would be the HX as the predominant form, which is effectively the conjugate acid. Okay, and so sometimes the picture is like you have to work out which one is the conjugate acid, which one's the conjugate base. You have to pay attention to what color it is. It will tell you in the question, and you work that out, and then you work out what's the predominant form. And that's it. Adios.